Now we'll look at those network covalent atomic solids. So carbon is a great example of this. Elemental carbon occurs or exists in several different forms. The ones you're most likely aware of are graphite and diamond, but there are other ones as well. So in graphite, what we've got is something like this, where we have carbon atoms covalently bonded to each other in these hexagon ring structures, but we have sheets of those. So here's a layer and another layer and another layer. And what holds the layers together are dispersion forces. So the layers are strong, but what holds them together is not strong, and that's what makes graphite slippery. And so you can use graphite as a lubricant. It makes an excellent pencil lead, because as you push it across paper, bits of it slide off and leave a mark behind. Graphite also conducts electricity. We have all these carbon bonds here. If you look at, which one's easiest to look at? Maybe this guy right here. How many electron groups around that carbon? How many other carbons is it bonded to? You can't see. So we have these hexagons, and then they're linked to other hexagons. So if we look at this guy right here, how many covalent bonds does it have? 3. So that would probably be sp2 hybrid, and then it's got a p orbital left over, right? So what happens with those p orbitals is they form a delocalized pi bond that extends across the whole molecule, molecular orbital theory. That delocalized pi bond is what allows graphite to conduct electricity. Graphite has a density of 2.2 grams per cubic centimeter. If you subject graphite to extreme pressure and temperature, you can change the structure of it and get a diamond. So a diamond now is also network covalent atomic solid consisting just of carbon, but now the covalent bonds extend in 3 dimensions. So the diamond has a higher density. The carbon atoms are closer together now. They're all covalently bonded. Here, the carbon atoms are each having, I know you probably can't see that, each carbon atom in here has 4 bonds. So what would the hybridization be? sp3. There's no extended pi bonding network. All of the electrons are occupied in making these sigma bonds, and so diamonds do not conduct electricity. It takes a lot of pressure, 50,000 atmospheres and 1,600 degrees Celsius. Yeah, so not necessarily economically feasible to make diamonds that way, but this is why diamonds are found deep underground, where natural pressures have caused them to form. Looking at how the atoms are arranged in a diamond, it is similar to the zinc blend unit cell. So here's a zinc blend. We had face-centered cubic, and the zinc ions were in 4 of those tetrahedral holes. In carbon, we have the same thing going on, except all of the particles are carbon atoms. So we have carbon atoms at the lattice points of a face-centered cubic, and the ones that are nestled in those tetrahedral holes are also carbon atoms. So each carbon atom is covalently bonded to 4 other carbon atoms. sp3 hybridization gives you a tetrahedral structure. And so each of these has a tetrahedral arrangement of its bonds, and that is what determines the crystalline structure. It can't do a cubic unit cell where it would have 90-degree angles, right? It's got to be in some sort of a tetrahedral arrangement. Diamonds have extremely high melting points, 3,800 degrees Celsius, because in order to melt, you have to break a lot of covalent bonds, and that's just not an easy thing to do. Diamonds are also extremely hard because of the covalent bonds. So diamond, besides being beautiful on a ring for that special someone, it's also very useful as an abrasive and a cutting tool. And so you can buy, saw blades that have diamonds on them. Now they're not, beautiful diamonds that you could take off and wear as jewelry, right? Little tiny diamond pieces. They conduct the heat well, so they conduct heat away from whatever you're cutting, and they're very hard, so they don't, wear down. There are some newer forms of carbon. We talked about one in the very first section, graphene. We talked about Friday night experiments and lateral ideas. Buckminster fullerene is another relatively new form of carbon. This was discovered in the 1980s by aiming a powerful laser at a carbon surface. So this is a ball made of carbon atoms covalently bonded to each other, and there are 60 carbon atoms in this. And it looks a lot like a soccer ball, except soccer balls have pentagons instead of hexagons. But it's a lot like a geodesic dome. Other numbers of carbons can also be made into clusters like this, and as a general class, they're called fullerenes, or the pet name for them is buckyballs. You can have as small as 36 carbon atoms to over 100 carbon atoms, and they form these little carbon balls. You can take the two-dimensional layers of carbon. Here's a graphene sheet. So we see these hexagons, and they're bonded in 2 dimensions all the way through. And so this is extremely strong, conducts electricity, again, because of that pi bonding network. You can take this and have narrow strips of it, so you can have these nano ribbons. You can form it so that it forms tubes. These are called nanotubes. And then you can have multi-walled nanotubes, where you have a bunch of these nestled inside of each other. This looks a lot like chicken wire, if you're familiar with chicken wire. These nanotubes, 100 times stronger than steel and 16 times less dense. So that's awesome, right? I know, right? What? This is why you go get, higher end golf clubs, and they're made out of graphite. It's like, what? Pencil lead? How does that work? Well, it's this sort of graphite. Carbon fibers. You can also use these to make very tiny wires. So really, really neat stuff. They use these in bicycles as well, bicycle frames with the carbon nanotubes. Okay, so leaving carbon behind, silicates. So these are extended arrays of silicon and oxygen. So now, this is an atomic solid because it does not contain individual molecules. But we have 2 different kinds of elements in here. Silicates are the most common network covalent atomic solid. They make up about 90% of the Earth's crust. Think sand. Sand is a silicate. So what we refer to as silica has a formula unit of SiO2, which makes you kind of think, well, those are SiO2 molecules, right? No, they're not. That's the ratio of silicon to oxygen, but they're actually covalently bonded 3-dimensionally. So if we look at the silicon atom here, how many valence electrons does silicon have? 4. So it can make 4 bonds, right? So it could make a single bond with each of these oxygen atoms. Are these oxygen atoms happy? No. They have a formal charge and they don't have a valence or an octet. So this oxygen is going to bond to another silicon. Now this oxygen's happy. It's got 2 bonds and 0 formal charge. And then this is going to be bonded, and you get the idea. So here's the 3-dimensional representation. Quartz is one form of silica. There's different forms. The silicon is bonded to 4 oxygens, and that would be an sp3 hybridization. It would form a tetrahedron. So here we see the silicon and the oxygens are arranged in a tetrahedron. And that goes on throughout the whole solid.